Hello students, this is lecture 4. Hopefully you have already watched lecture 3. If not, please go back and watch that lecture first. Homework due 2 is due Tuesday, September 5th. See the handout on Blackboard for that. You should be able to submit it the same way you did as your homework last week. Today we're moving into new material. We're talking about Exergy in chapter 8. So we're looking at the first few sections of chapter 8, sections 1 through 4. And we're going to talk about Exergy, which is also known as work potential or availability. So in that discussion, we're also going to talk about reversible work and irreversibilities, as well as second law efficiency. You'll find Exergy, or the discussion of Exergy, to be somewhat analogous to this, the discussion of entropy, but it's a little bit easier to follow and a little bit easier to understand. So hopefully you had a nice refresher on entropy, you've done a little bit of background reading, and then this will hopefully make sense to you and we'll be able to proceed forward. When we look at the energy resources of the world, it's important to recognize that the limitations on those energy resources can cause us to really look and re-examine the energy policies that are in place. So, there have been numerous laws passed to try to limit the production of unhealthy byproducts due to burning fossil fuels. There have been incentives to go towards a more renewable energy. And as we consider all of these options and as we look at our sources of energy, both from a clean engineering standpoint and also from an energy production standpoint and an economic standpoint, we have to use smart engineering design to really help us eliminate waste, improve conversion efficiencies, and to develop new technologies. So this discussion of Exergy today will hopefully allow you to look at a resource, look at an energy source, and be able to determine how much energy you can feasibly obtain from this particular resource. Because even though it may seem that a certain technology is better than another, if you look at it from an economic standpoint or an environmental standpoint only, you don't get the entire picture. So looking at things from an Exergy standpoint is actually a helpful tool, and it allows us to make a better, more informed decision when we're implementing energy strategies. So Exergy is the work potential of an energy source, and it's a function of both the system and also the environment that is surrounding the system. And we'll discuss a little bit more about that in detail in the coming slides. As governed by the second law, there's an upper limit on the amount of work that any device will deliver. So even if we, purport to have some device that has infinite free energy, there's probably actually an upper limit to it that we just have not recognized or realized. And then any reversible system or process will deliver the most usable energy. So when we look at an energy source from the Exergy standpoint, in many cases we're looking at operating a reversible system in between that energy source and the environment so that we can get the best case scenario and see how much is possible. So as we proceed with this discussion, it's important to define a few terms. The first is dead state. And the dead state is the state at which your system is in thermodynamic equilibrium with its surroundings. So thermodynamic equilibrium means that it is in thermal equilibrium, pressure equilibrium, chemical equilibrium, mechanical equilibrium. All of those four must be satisfied in order to have complete thermodynamic equilibrium. Surroundings are the area outside the border of your system. And this time we're also going to look at immediate surroundings, which is the portion of the surroundings that is affected by the process itself. So it's the surroundings that are immediately around your system or your device. And then the environment is everything else. So it's the portion of the surroundings that is not affected by the process at all. If we look at the system and the surroundings, you can see that we have our system here, which let's just assume is a potato. So the system has some properties to it, and it's surrounded by this system boundary, which defines the edge of the system. So the immediate surroundings are immediately adjacent to the system boundary, and whatever is going on within the system itself will have an effect on the immediate surroundings. And then the environment is outside that particular area, so any processes ongoing in the system will not affect this environment. So there won't be any temperature changes or pressure changes due to what's happening in the system. And any irreversibilities that occur in the system or in this process will occur within the system and the immediate surroundings itself. So we'll assume that nothing really affects the environment, but if anything were, it would be a reversible process so that we could reverse it and have no undue effect on the environment. So exergy change is calculated from the current state of our system to some final state along a reversible path. And the total exergy available is calculated using the dead state as the final state. So we may have some process that occurs from state 1 to state 2, but at the end of state 2, it's not yet in thermodynamic equilibrium with its surroundings. That would not tell us the total exergy change. That would just tell us the exergy change from state 1 to 2. If we want the total exergy change, we go from state 1 all the way to the dead state. So we use the dead state as the final state. And the properties at the dead state are all given this subscript 0. So T0, P0, V0, H0, S0, etc. And unless it's otherwise stated or specified in a problem, we can assume the dead state to be 25 degrees Celsius and 101.325 kilopascals, or in other words, just normal temperature, normal atmospheric pressure. Mechanical energy from kinetic and potential energies is available to be converted to work 100%. So mechanical energy can be thoroughly and completely converted to work. Thermal energy cannot, as we'll discuss later. So if we're trying to determine the exergy of kinetic energy, it's just equal to V squared over 2. And you notice that this total exergy of kinetic energy is just V squared over 2 because at the dead state, we'll assume that our system has no velocity. And similarly, it will have no potential to change in elevation. So we could subtract off V minus V sub 0, both of those terms squared, but V sub 0 by necessity at the dead state is 0. So we just take this term V squared over 2, and then the same for potential energy. It's just the gravitational constant multiplied by Z, which is our elevation at our initial location. So let's do an example. And in this case, we have a furnace that can supply heat steadily at a temperature of 1300 Kelvin and a rate of 500 kilojoules per second. So we want to determine the maximum amount of power that can be produced using the heat supplied by this furnace if we assume that the temperature of the environment is at 300 Kelvin. So let's take a look at that. And we have our example here. So in order to extract any usable work from this furnace, we have to put a heat engine between it and the environment. So the furnace is at 1300 Kelvin and the environment is at 300 Kelvin. And we want to determine how much usable work this furnace can supply. So we have our heat engine set up, and we want to determine the thermal efficiency for a reversible heat engine between those two locations. So in order to do that, we just do 1 minus T sub L over T sub H. And in this case, our T sub L is our dead state of 300 Kelvin. So we calculate our thermal efficiency to be 0.7692, which is about 76.9%. We also know that the thermal efficiency of a reversible heat engine is equal to W dot max over Q dot in. So we're told Q dot in that the furnace can supply 500 kilojoules per second. This is not an energy term, this is power. So it's power over time, 500 kilojoules per second. So if we put that into our equation, we can find the max power output from this heat engine would be Q dot in times this reversible thermal efficiency. So we find that the max power output that we could obtain from that furnace is 384.6 kilowatts. Okay, so again, this exergy is calculated using the temperature of the furnace and how much heat it can supply, and then the known temperature of the environment. So if we were to put a heat engine in between those 2 points, that is how we determine the max amount of available power we can get from that particular furnace. Reversible work is the max amount of useful work that can be produced, or it is the minimum amount of useful work that must be consumed as a system undergoes a process between an initial and a final state. So if we perform that process in a totally reversible manner, then we can determine how much work must be consumed or how much work can be produced by that reversible system. And if we use the final state as our dead state, or if we assume that the dead state is going to be the final state, then our reversible work is the same as the exergy for that process. So again, the final state can be any point between the dead state and the initial state. But if the final state is equal to the dead state, meaning there's no other additional energy that can be extracted from this system because it's at thermodynamic equilibrium with its environment, then our reversible work is equal to our exergy. So that's how we determine the potential energy possibilities of a system. Because if that system is not in thermodynamic equilibrium, let's say there's a pressure differential between the system and our environment, or a temperature differential, there's still some usable work that can be extracted. It may not be a lot, but anytime your system's not at equilibrium with the environment, it has the potential to do work or to consume work. So surroundings work is the work required to move the atmosphere during a process. And this is work that cannot be recovered. It's considered lost work. So if we think about a piston cylinder device, and if we're expanding the gas inside that piston cylinder device, there's some work that has to be done to move the atmospheric air out of the way. So the surroundings work is considered not wasted work, but it's considered work that's lost during an expansion process because our system has to work even harder against the atmosphere in order to push to expand. And then during a compression process, it's actually considered a gain because the atmosphere is actually helping to compress the gas that's inside of our cylinder. Now, this surroundings work is only valid for a volume change process because it's a boundary work phenomena. And it's not valid for system cycles because a cycle would presumably return to the initial volume. So this net change in volume would be 0. So the surroundings work is equal to the pressure of the dead state multiplied by the change in volume of our system as it goes from state 1 to state 2. Useful work is the actual work done minus the surroundings work. And again, as I mentioned before, the surroundings work is going to be a positive quantity for an expansion process, and it's going to be a negative quantity for compression process. So it's actually going to serve to increase our quantity of useful work. So if our volume 2 is greater than volume 1, then this surrounding work is positive, which means it subtracts from our useful work. And if our volume 2 is less than volume 1, then the surrounding work is negative, which means that it adds to our actual work to give us an even greater term for useful work. Irreversibilities are the difference between the reversible work and the useful work. So when we're calculating this useful work, it's the amount of work that we actually can get use of out of our system. So if we have a completely reversible system, then our irreversibilities are 0, and our reversible work is our useful work. However, in the real life, we have to account for irreversibilities. So if we have a net work output, we need to subtract off the useful work to determine the irreversibilities. But if our system is consuming work, then we use the useful work minus the reversible work, because irreversibility is always a positive quantity. And another term for this is that it's the exergy destroyed. So in Chapter 7, when we talked about the entropy generated, it's analogous to this term exergy destroyed, because when we're destroying exergy, we're destroying the ability or the potential for the system to do even more work. So it's another way of looking at irreversibilities as taking away from our system the potential to use that energy in another way. Instead of, needing to put in a greater power input to overcome friction, if we can reduce the friction, then that power output can be useful in another manner. So again, if a process is reversible, there are no irreversibilities. I is equal to 0, and our reversible work is equal to our useful work. And for a work-producing system, the reversible work is greater than the useful work. And for a work-consuming system, the reversible work is less than the useful work. So let's do another example to look at and calculate the reversible work input and the irreversibility. So if we go to our second example in lecture 4, we have a house that's losing heat at a rate of 50,000 kilojoules per hour when the outside temperature of the environment is 4 degrees Celsius. We want to heat this house using electric resistance heaters. So if the house is to be maintained at a constant temperature of 25 degrees Celsius at all time, we need to determine the reversible work input for this process and then also the irreversibility. Okay, so another way of looking at this problem is saying, okay, right now we're using these electric resistance heaters to heat our home. And in order to replace the heat that's lost, we have to input a work of 50,000 kilojoules per hour. And this is actually a power input, so kilojoules per hour would give us a term of watts. So in order to make up for these losses, we're using this resistance heater, which has a 1-to-1 replacement value. However, if we used a reversible heat pump instead, we can look at what the work requirement would be. And then when we find the difference between the two, that's how we determine our irreversibility, or the losses that are assumed as we perform this process. Okay, so to calculate this reversible work, or this reversible power input, we use a reversible heat pump. And the coefficient of performance for a reversible heat pump is 1 over 1 minus TL over TH. And again, we need to use Kelvin in this equation. So T sub L is our environmental temperature at 4 Celsius, which is 277 Kelvin. And T sub H is the temperature of our home at 298 Kelvin. So we calculate our coefficient of performance for that reversible heat pump and find that it is 14.19, which is pretty high for a heat pump. Now we know that the coefficient of performance for a heat pump is also equal to Q dot H over work dot in. Q dot H is the amount of heat that we need to supply to our home in order to make up for the losses outside. So Q dot H is equal to this 50,000 kilojoules per hour, which if we convert it to kilowatts is 13.89. So we just divide through by 3,600 seconds to convert it to kilowatts. Now if we divide our Q dot H by our COP, then we'll find how much reversible work we're putting into this system. So 13.89 divided by the COP is equal to 0.979 kilowatts. Okay, so replacing our electric heater with a heat pump will require us to only spend 0.979 kilowatts in power. So to determine our irreversibility, we can take our useful work in, which is this 13.89 kilowatts that we're using our electric resistance heater, minus the 0.979 kilowatts of our reversible work. And so we find that there's an irreversibility associated with this process of 12.91 kilowatts. So if you look at this process, an electric resistance heater takes 100% of the electricity and converts it to heat. What this is saying is that once we've converted that to heat, there's an irreversibility associated with it in the form of 12.91 kilowatts. So we can never convert that heat entirely back to electricity. We can do some of it with the heat engine, but it's just not possible to regain that heat in a similar fashion. So if instead we're taking a little bit of electricity and some heat in order to heat our home, so 0.979 kilowatts versus 13.89 kilowatts, then we would have a much smaller irreversibility associated with the process. So our irreversibility in this case with a reversible heat pump would be 0. But if we wanted to find the irreversibility associated with a real actual heat pump in our home, then we would perform these calculations again using the actual coefficient of performance for our real heat pump and then compare our performance to the reversible heat pump. So in essence, using the electrical resistance heaters wastes 12.91 kilowatts as compared to a reversible heat pump. The first law, efficiency, or the thermal efficiency, tells us how effective a system is at converting energy. The reversible thermal efficiency tells us the best possible theoretical thermal efficiency. And then the second law, efficiency, tells us how the given system will stack up according to its own best theoretical performance. So we take the thermal efficiency and divide it by the reversible thermal efficiency to give us the second law efficiency. So this is another way of comparing systems one to another, because if you just compare thermal efficiencies, it's somewhat misleading. But if you look at a thermal efficiency and compare it to its reversible thermal efficiency, then you get a clearer view of how well your system is doing according to the second law of thermodynamics. So this second law efficiency, just dividing these two one by another, gives us that value. So let's look at that. Consider the two systems at left, both with a thermal efficiency of 30%. That's just given to us in the problem. Which one is the better system? Well, according to this, they both have an equivalent thermal efficiency, 30%, so you might think, oh, well, they're both equivalent systems. Well, that's not the entire picture. So let's look at the reversible thermal efficiency. For the system A, we can see that the reversible thermal efficiency is just 1 minus T sub L over T sub H, or 1 minus 300 over 600 Kelvin, which gives us a thermal efficiency of 50%. Heat engine B has a thermal efficiency of 70%. So again, we ask, which one is the better system? If you're just looking at the reversible thermal efficiencies, you might think, oh, of course, this is a better system because it has a higher thermal efficiency. But still, that's not the total picture. What we need to do is compare their actual performance with their theoretical performance in the form of the second law efficiency. So if we calculate the second law efficiency of heat pump or heat engine A, we find that it's 60%. And for heat engine B, it's actually 43%. So because heat engine B has a higher theoretical thermal efficiency, it actually doesn't perform as well when we stack it up against the system with a lower thermal efficiency from a theoretical standpoint. So again, it's important to take these numbers and put them in a useful form, which allows us to really truly analyze them and compare them one to another. So in general terms, if we want to calculate our second law efficiency, for work producing devices, we can use the thermal efficiency over the reversible thermal efficiency, or we can say that it's the useful work divided by the reversible work. And then for work consuming devices, it would be the reversible work divided by the useful work. And for refrigerators and heat pumps, we use, instead of thermal efficiency, coefficient of performance. So it's the coefficient of performance of the actual refrigerator or heat pump divided by its reversible coefficient of performance. The second law, efficiency, can never exceed 100%, and this is even true for heat pumps and refrigerators. So although a coefficient of performance can be greater than 1, when you're dividing through a coefficient of performance by its reversible coefficient of performance, which is always going to be greater than our actual coefficient of performance, then you can see that this quantity should always be less than 1. When we're determining the second law efficiency, we must determine how much exergy is expended or consumed during a process. So for devices that don't consume work or produce work, we can also calculate a second law efficiency in the form of the exergy recovered divided by the exergy expended. And another way to look at that is 1 minus the exergy destroyed over the exergy expended. And again, the exergy destroyed is the same as the irreversibility of the process. So for a heat engine, the exergy expended is equal to the exergy of the heat supplied minus the exergy of the heat rejected, and then the exergy recovered is equal to the work net out. For a refrigerator or a heat pump, the exergy expended is equal to the work net in, and the exergy recovered is equal to the exergy of the heat source coming in to a heat pump or the heat source at Q sub L for the refrigerator. And for a heat exchanger, the exergy expended is the decrease in the energy of the hot fluid, and the exergy recovered is the decrease in the exergy of the cold fluid. For an electric resistance heater, we do it a little bit differently, where the exergy expended is equal to the work of the electric heater, or the electrical work, and then the exergy recovered is the exergy of the amount of heat that's added to the room. And another way to calculate that would be this Q dot, which is the rate of heat added to the room, times 1 minus T0 over TH, where TH is the temperature of the room, and T0 is the temperature of the outdoor space or the atmosphere surrounding. And then the W dot E is just the electrical work input to the system. So let's do another example. Calculate the second law efficiency of a heat engine that receives 800 kilojoules of heat from a source at 1500 Kelvin and rejects 500 kilojoules of heat to a sink at 300 Kelvin. So let's look at this example. It's example 3. So if we want to calculate this second law efficiency for the system at left, the first thing we need to do is calculate the thermal efficiency and the reversible thermal efficiency. So you can do those in either order, but if I calculate the reversible thermal efficiency, I just need to know the temperatures of the reservoirs. So it's 1 minus T sub L over T sub H, which is 1 minus 300 Kelvin over 1500 Kelvin, and I get 0.8 for the reversible thermal efficiency. Similarly, the thermal efficiency is 1 minus Q sub L over Q sub H, or 1 minus 500 over 1 minus 500 over 800. So my thermal efficiency there is 0.375. Now if I just divide those two numbers, the thermal efficiency divided by the reversible thermal efficiency, I get 0.375 over 0.8, which is 0.469 or 46.9%. So exergy is a combination property because, as we mentioned before, it depends not only on the state of the system, but also the environment surrounding the system. So the environment will determine your dead state and the temperature and pressure at which you would be in thermodynamic equilibrium. So anything that's in equilibrium with its environment has zero exergy. And we can say that a system is in thermomechanical equilibrium. To simplify the analysis, this is also called a restricted dead state. So what we're looking at in thermomechanical equilibrium is that the temperature and pressure of the system are in equilibrium. We may be ignoring any kinetic or potential energy effects. We may also be ignoring any chemical reactions that are ongoing or any mixing that is occurring between the system and the environment. So thermomechanical equilibrium is sufficient for the analysis that we do within this class if we just look at the temperature and the pressure being in equilibrium with its environment. Okay, so when we're looking at two different types of system, a closed system versus an open system, the analysis is slightly different, but they are related. So we're going to go through the closed system exergy analysis so you can see where all the terms come from and how this analysis comes about. So it's related to the work done, the heat transfer, and the entropy in the system. So we're first just going to look at a piston cylinder device, and we're going to imagine that it's connected to a reversible heat engine. Okay, so there's some heat that's leaving this piston cylinder device, and it's being used to power a heat engine between the system and the environment. So there's some work that's occurring. So we're applying a force to this piston cylinder device to move this piston, and there's some useful boundary work that occurs because of that process. So we start off with our basic energy equation, where we're doing this in differential terms because we're causing a differential amount of movement to occur in the system. So we have del E in minus del E out is equal to the total change in energy of the system. And this total change in energy is not a partial differential because it's a total differential. It's a quantity that can be fully differentiated by time. Okay, so we can rewrite this E in and E out in terms of Q and W. So we say this negative, this del Q minus del W is equal to del du of the system. So it's a Q out and a work out. That gives us negative terms. So the in goes away. We're just looking at the outputs at this point. So first we want to find this term, del W. So if we look at this boundary work that's ongoing, it's equal to PdV. But there's two components to it, because we have some boundary work within our system as it goes from P to P0, and we also have some boundary work that's occurring outside our system at a constant pressure of P. So there's work to move this atmospheric pressure, and then there's also work that's being done in the system as our pressure is going from the system pressure initially to the environmental pressure. So we have this boundary work, which is P minus P0 times dV, and we're assuming it's a linear change in pressure, so we don't have to know how the pressure varies with distance or as this piston is moved. And then we have the surroundings work term. So our total boundary work is equal to this boundary work plus the surroundings work. We can say that this term is just the useful boundary work, because that's the useful boundary work that's ongoing within our system. So we can find that del W is equal to this del WB, or this useful boundary work, plus the surroundings work, which is P naught times dV. Okay, so now we want to find del Q. So in this case, del Q is equal to this del work of the heat engine plus this del Q of the heat that's being rejected to the environment at T0. So we can look at the ratio between the two. For a heat engine, a reversible heat engine, we know that the ratio between these heat terms is equivalent to the ratio between the temperatures. So del Q naught over del Q is equivalent to T naught over T, which means that we can say that del Q naught is equal to del Q times T naught over T. So this del Q term is equal to this the work of the heat engine plus this del Q naught term, which we solved for and determined was T naught over T times del Q. Now we also remember from our discussion and study of entropy that del Q over T, this del Q over T is equal to negative ds, or ds is equal to negative del Q over T. So we can replace this part of the equation, that del Q over T, with ds. And it's a negative ds because of the way that entropy is defined. So we now have this del Q is equal to del work of the heat engine minus TdS. So let's substitute del Q and del W back into this top equation here and collect terms. So if we collect them and rearrange, then we have the work of the heat engine plus the boundary work, or the useful boundary work, is equal to negative du minus P naught dV plus TdS. Okay, so we can flip the negative sign. We recognize that the total useful work is equal to the boundary work minus the, oh no, so we flip the negative sign in here. So the work of the heat engine plus the useful boundary work is the total useful work from this combined system. And it's equal to the change in state from U to U1, P0 times V to V1, and T0 times S to S1. Okay, so this is the long kind of drawn out derivation of how we get an equation for the total useful work, which is also known as the exergy. Okay, so in this form we have all capital letters, so it's not per unit mass, it's multiplied through by the mass. So we would have units in terms of kilojoules. We can write it in a couple of different ways. So this is, again, the total useful work, or the exergy, is equal to these terms, which we derived on the previous slide. So this U minus U naught, V minus V naught, and S minus S naught. And then we can also add back in the kinetic energy and potential energy terms to find the total exergy of a closed system. Similarly, we could do it on a unit mass basis where we divide through by the mass, or if we wanted to combine this delta U term with the velocity and the gravitational terms from kinetic and potential energy, we can just call all of those E. Okay, so U plus V plus G is just equal to E minus E naught. And if we wanted to find the change in exergy, delta X is equal to X2 minus X1. So if we assume that X is X2 is our dead state, then we'd have the same equation as we do up here. But otherwise, we can just plug in this X2 minus X1, and we get the U2 minus U1, V2 minus V1, S2 minus S1, et cetera, et cetera, et cetera. Okay, so that's how we would calculate the exergy change in any system. And then again, if we assume that our final state is our dead state, then it just returns to looking like this equation here. So let's do an example. So a closed system exergy analysis. 5 kilograms of helium undergoes an expansion process from an initial state of 75 Celsius and 2 meters cubed per kilogram to a final state of 10 degrees Celsius and 3 meters cubed per kilogram. We're to assume the surroundings are at 25 Celsius and 100 kilopascals. So we need to determine the change in the useful work potential of the helium during this process. So since this is a closed system, we can use the closed system exergy analysis, and we're given a mass, so we can use it in this form and then multiply through by the mass, or we could do it in this form directly. So let's look at that example. This is example 4. So if we look up the property values for helium in the back of the book, table A3, we find the R value is 2.0769 kilojoules per kilogram Kelvin. And going from 10 degrees Celsius to 75 degrees Celsius, the average temperature is approximately 300 degrees Kelvin. So we're going to use C sub V at 300 Kelvin in our calculations. So we're to assume the surroundings are at 25 Celsius, 100 kilopascals, and we're going to neglect any change in kinetic or potential energy during this process. So we found that our change in exergy is just equal to U2 minus U1 plus P naught V2 minus V1 minus T naught times S2 minus S1. Now we don't really have good tables for helium to look up this S2, this S1, or U2, U1, so we can make some additional approximations. We can convert or we can use the specific heat approximation in order to calculate our change in internal energy using C sub V at an average temperature times T2 minus T1. And in order to calculate our change in entropy, for an ideal gas, we can use the Gibbs equation. So this is, I believe, the first Gibbs equation, which allows us to calculate our change in entropy using this equation, C sub V average times the natural log of T2 over T1 plus R times the natural log of V2 over V1. So now we can just start plugging in the numbers. So we have C sub V, we know our delta T, so I've converted everything to Kelvin just to keep things straight. Our P0 is 100 kilopascals. Our change in volume goes from 3 meters cubed, or it goes from 2 meters cubed per kilogram to 3 meters cubed per kilogram, so V2 minus V1. And then we know our T naught is 298 Kelvin. So again, we put in C sub V, natural log of T2 over T1, and R, natural log of V2 over V1. So if we plug in the numbers for that, we find that our exergy is negative 161.501 kilojoules per kilogram. Or if we multiply through by the mass, which in this case was 5 kilograms, then we find that our total exergy change is negative 807.51 kilojoules. Okay, so I said before we can not have a negative exergy or a negative irreversibility, but we can have a negative change in exergy, meaning that our exergy has decreased. So going from the initial conditions of the helium to a more expanded state where our temperature decreases and our pressure decreases, then we find that we've lost some of the ability to do work during that process. And I calculated the pressure change just for my own curiosity, that we were originally at 361 kilopascals and it decreased to 206.3 kilopascals. So this decrease in temperature, decrease in pressure, made it so that our helium has less ability to provide any sort of work to us. So we have an exergy decrease of 807.51 kilojoules when we compare the initial state of the helium to the final state of the helium. Okay, so let's look now at the open system analysis. So the exergy of a flow stream is going to be equal to the exergy of a fluid that is not flowing, like we might find in a closed system, plus the exergy associated with the flow of the fluid itself. So when we start off with the exergy of the non-flowing fluid, this is identical to the equation that we used in the closed system case. So we have U minus U naught plus P times V minus V naught minus T times S minus S naught plus the V squared over 2 plus GZ. Now we have this additional term that is the exergy of flow. So if you're looking at this, this may seem similar to you, to the way that we derive the energy equation for a closed system versus an open system, that we had this one term which represents the latent properties of the system and then an additional term that represented the flow energy. This is similar. We're just doing it with exergy instead of energy. So we now have this additional term on this this part of the equation, the P minus P naught times the volume. So the change in pressure times the volume is like analogous to a flow work, but we're looking at it as flow exergy. So when we add that term onto the equation, we find that it actually cancels out with this part of the equation. So we can collect terms and rearrange. We find that we have this U plus PV minus U naught plus PV naught minus T times S minus S naught plus the V squared over 2 plus GZ. Looking at this here, this may seem to you like a term we've seen before, and it is. It's enthalpy. So we can combine this U plus PV term into H, or enthalpy, and the same for the U naught plus P naught V naught. So this is the exergy of a flow stream, and it's represented here very similar to the exergy of a closed system, except for we use enthalpy now instead of internal energy. So that takes into account the exergy of the fluid as it flows through the system. Again, so fluid has some intrinsic energy or exergy associated with it, and then when that fluid is moving, it has some additional energy or exergy associated with it. Okay, so this is analogous to the energy balance, very similar to how we derive those equations. We can also look at this from state 2 to state 1, very similar, and we could look at it on the per unit mass base as we have here, or if we multiplied through by the mass, then all of these would be uppercase letters. So let's do an open system exergy analysis. And this will be the last example for today as we go through and look at this turbine. So we have a turbine with combustion gases entering at 900 Celsius and 800 kilopascals at a velocity of 100 meters per second. Then they leave the system at 650 Celsius, 400 kilopascals, and 220 meters per second. So we want to determine the exergy of the combustion gases at the inlet and at the outlet, assuming that the surroundings are at 25 Celsius and 100 kilopascals. And because combustion gases are a combination of several different gases, we are given a C sub P and an R for those, which is similar to the C sub P and the R for air, but slightly different because it has other chemical components to it. So it's slightly decreased. So if we look at this example, it's example 5 from this lecture, that we've set it up like such. So we have our combustion, our gas turbine, which has combustion gases flowing through it, have the initial conditions of the inlet, we have the final conditions of the outlet. Okay, so we want to determine this exergy of flow 1 and the exergy of flow 2. We're going to neglect any the changes in potential energy because no information is given to us about the change in potential energy. We're also going to assume that it's steady flow and that these combustion gases behave very much like an ideal gas. So we just set up the equation as such that the exergy at the inlet is equal to the enthalpy of the inlet minus the enthalpy of the environment. And then we subtract off T naught times S minus S naught, so the entropy difference between the inlet and the environment. And then the velocity of the inlet compared to the velocity of the environment, which in this case is 0. So we just have a v squared term. And then our potential energy goes to 0. So again, we make some approximations using the ideal gas law and the assumptions that can often come along with that. So we're assuming that H minus H naught is C sub P times T minus T naught, and that this change in entropy, now we use Gibbs' second equation, where we use C sub P, that's a natural log, the L is not showing very well, of T1 over T naught minus R natural log of P1 over P naught. And then it's plus this velocity term squared over 2. So if we start plugging in the numbers for that, again, being careful to use Kelvin in our analysis, making sure that this T naught gets applied to both terms. So we multiply it by everything inside this equation here. And then being very, very careful with units, because the units on velocity squared over 2 is meters squared per second squared. Okay, that is not equivalent to a kilojoule per kilogram. It's off by a factor of 1,000. Okay, so we can combine these terms after we've converted the units of this velocity squared term. So 5,000 meters squared per second squared, multiply it by the unity conversion ratio of 1 kilojoule per kilogram over 1,000 meters squared per second squared, because a kilojoule per kilogram is equal to 1,000 meters squared per second squared. So if we plug in all the numbers on that, we find that the exergy of the inlet is 705.9 kilojoules per kilogram. So part B, again, a very similar analysis, where now instead we're looking at the enthalpy of the outlet as compared to the enthalpy of the dead state, or the state of the environment. So we can plug all of these numbers in, again, being careful that we multiply through, we distribute our T0, that we convert the units properly. Again, using Gibbs' second equation allows us to find the change in entropy for an ideal gas, assuming constant average specific heats. So we plug in all the numbers for that, convert from meters squared per second squared to kilojoules per kilogram, and we find that the exergy at the outlet is equal to 466.1 kilojoules per kilogram. So if we wanted to be, very thorough, we could find the difference in entropy or exergy from the inlet to the outlet. We could subtract 705.9 minus 466.1, and we'd find something on the order of 240 something kilojoules per kilogram. We're not given a mass flow rate, so we leave it in the per unit mass terms as you see there. Okay, so that's the lecture for today. I encourage you to go through the homework. You probably also want to actually read the chapter section 8.1 to 8.4. This video is a little bit shorter than a normal class would be, just because working through the examples goes quickly when they're already written out, which makes up for the last video being a little bit longer. But I want you to really read ahead so that you can understand these concepts when we're talking about them in class. Okay, so if you have trouble understanding entropy, you might find this to be a little bit easier, but I still would like you to read and study and try to understand the concepts and not just always look for an equation to start plugging numbers into. So get working on your homework. If you have any questions, please email me. I hope that you're helping one another, working together in my absence, but not copying, of course, because that would not be okay. Be prepared for a quiz on Tuesday when we get back, and I will see you on Tuesday.